Hello everyone and welcome to Control and Estimation Tutorials. This is the third part of the tutorial series on particle filters. In this third tutorial part, we explain how to implement the particle filter algorithm in Python from scratch. Here is a brief summary of all three parts. In part 1, we presented the problem formulation for estimating the state of a dynamical system by using the particle filter. In part 2, we derived the particle filter algorithm. More precisely, we derived the bootstrap particle filter algorithm, which is also known as the sequential importance resampling or SIR filter. You're currently watching part 3. The links to all three tutorial parts are given in the description below this video. By the end of this video tutorial, you will learn how to implement the particle filter algorithm in Python from scratch. To test the particle filter algorithm, we use a second-order mass spring damper system. This system has two states, position and velocity. We will use the particle filter algorithm to estimate the complete state by only observing the position. By the end of this tutorial, you will learn how to generate this graph and this animation. The graph shows the estimated state trajectory obtained by using the particle filter as well as the true stochastic state space trajectory. The animation on the right shows how the particle filter is tracking the state of the system. This animation represents the state trajectory in 2D state space. That is, every point is a state. The true state is represented by the red circle. The particles are represented by colored circles. The weight of the particle is proportional to the radius of the circle. That is, the radius of the circle is the probability of the state being at the particular point in the state space. The higher the radius, the higher the probability. But before I start with explanations, I need to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as almost 500 free video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Okay, let's start. Here, for completeness, we provide a brief summary of the particle filter algorithm. As explained in the first tutorial part, not to blur the main ideas of particle filters with too many mathematical details, in this tutorial series we derived the particle filter algorithm for linear state space models. However, everything explained in this video tutorial can be generalized to nonlinear systems. The particle filter is derived for this state space model. Here, xk is the state vector at the discrete time step k, uk-1 is the control input vector at the discrete time step k-1, wk-1 is the process disturbance vector or process noise vector at the discrete time step k-1, yk is the observed output vector at the discrete time instant k, vk is the measurement noise vector, and a, b, and c are the system matrices. We assume that the process disturbance vector wk is normally distributed with zero mean and with a covariance matrix equal to q. Also, we assume that the measurement noise vector vk is normally distributed with zero mean and the covariance matrix equal to r. Under these assumptions, in the first tutorial part, we have shown that the state transition density or the state transition probability density function, that's usually denoted like this, is normally distributed with this mean and the covariance matrix equal to the covariance matrix of the process disturbance vector wk. That is, the state transition density is a density of the following normal distribution. Also, in the first tutorial part, we have shown that the measurement density or the measurement probability density function, that's usually denoted like this, is a normal distribution with a mean equal to c times xk and the covariance matrix equal to the covariance matrix of the measurement noise vector vk. That is, the measurement density is a density of this normal distribution. To implement the particle filter algorithm, we need to draw samples of xk from the state transition probability given by the equation number 4. There are two approaches that can be used to generate these samples. The first approach that we use in our Python implementation is to draw random samples of the process disturbance vector Wk from its distribution given by the equation number 2. After that, we can use this generated sample, the value of xk minus 1, and the value of uk minus 1, and the state equation to compute the sample of xk. The sample of xk generated in this way is distributed according to the state transition probability given in the equation number 4. Another approach for generating xk is to directly draw samples from this distribution. At every discrete time instant k, the particle filter computes the following set of particles. A particle with the index of I consists of the tuple xk with the index I, wk with the index I, where xk with the index I is the state sample and wk with the index I is the importance weight. The set of particles approximates the posterior density, denoted like this, by using this equation. That is, the posterior density is approximated as the finite weighted sum of wki and this function delta. This function delta is the Dirac delta function that is shifted and centered at xki, that is, at the sample of the state. To summarize, the goal of the particle filter is to estimate the set of particles given by the equation number 6 that approximates the posterior density given by the equation number 7. By approximating the posterior density, we can easily compute the state estimate or any other statistics such as variance, mode, confidence intervals, etc. For example, as we will show later on in this tutorial, once the posterior density is approximated, the state estimate can be computed by computing a simple weighted sum of particles. Here is the brief summary of the SIR or bootstrap particle filter algorithm. For the initial set of particles, denoted like this, we perform the following steps for k is equal to 1, 2, 3, 4, etc. In step 1, by using the state samples from the previous time step k minus 1, that is, by using xk minus 1 with index I, we generate n state samples at the time step k and that are denoted by xk with the index I. These samples are generated from the state transition probability with the density denoted like this. In step 2, by using the observed output yk and the weight wk minus 1 with the index I that is computed at the previous time step k minus 1, we calculate the intermediate weight update denoted by wk hat with the index I by using the density function of the measurement probability and by using this equation. After all intermediate weights wk hat with the index I are computed, we compute the normalized weight wk with the index I by using these two equations. That is, we first compute the sum of the weights and then we compute the normalized weight by using this equation. After step 1 and step 2, we computed the set of particles for the time instant k. That is, we computed this set. Here is step number 3. This is a resampling step. This step is performed only if the following condition is satisfied. First, we compute this constant called n effective. The constant is computed like this. If n effective is smaller than n over 3, and to remind you, n is the number of particles, then we need to resample the particles. That is, we take the particles from our original set, we randomly select them according to the criterion that we will explain in the sequel, and we form a new set of particles out of the old set of particles. Before we explain the Python implementation of the particle filter algorithm, we first need to explain the resampling step, since this step plays a crucial role in particle filtering. The idea of resampling is to select particles from the set of particles computed after step 1 and step 2. That is, we want to select n particles with replacements from this set, and to modify the weights. This will be explained in the sequel. There are several types of resampling approaches. The most basic resampling approach is to draw a new set of state samples such that the probability of selecting a particular state sample is proportional to the weight of the sample in the original set of particles. Let us explain this with an example. Let us assume that we have a set of 3 particles. First particle, second particle, and the third particle. Here, for simplicity, we assume that the states are scalars. We want to select a new set of 3 states from this set. The new set of state is selected such that the probability of selecting a particular state is proportional to the weight of the state in the original data set. For example, since the weight wk3 of the state xk3 has the largest value that is equal to 0.5, then the resampling procedure should be designed such that there is a 50% of chance to select the state xk with the index 3. Similarly, the resampling procedure should be designed such that there is only 10% of chance for selecting xk with the index 1. This is because this state has the weight of only wk with index 1 equal to 0.1. Similarly, the state xk2 equal to minus 0.1 should be selected with a probability of 40%. This is because of the weight that is equal to 0.4. For example, if the resampling procedure is properly designed and if you repeat the resampling process many times, we might obtain sets of states that look like this. In the first selection experiment, we might obtain the following set: xk3, xk3, and xk2. Then, in the second selection experiment, we might obtain this set: xk2, xk3, and xk2. In the third selection experiment, we might obtain this set: xk2, xk3, and xk3. Notice over here that during the first 3 selection experiments, we didn't draw a sample of xk1. This is because the weight corresponding to xk1 has the value of only 0.1. That is, we only have 10% of chance of drawing xk1. This is very important to keep in mind. Then, maybe after 15th selection step, we will actually draw xk1 and this set xk1, xk2, and xk3. Let us now explain what happens next after we select the states. As an example, let us use the set of states from the first selection experiment. That is, let us use the set consisting of xk3, xk3, and xk2. After we selected the states, we need to relabel them. For example, after the first selection experiment, we would relabel the states as follows. xk3 will become xk-1 in the new set, xk3 in the old set will become xk-2 in the new set, and xk2 in the old set will become xk-3 in the new set. Consequently, we have a new set of states xk-1, xk-2, and xk-3. The next step is to assign uniform weights to the new set of states. Since we have 3 particles in the original set, the value of all weights should be 1 over 3. That is, we assign wk-1 is 1 over 3, wk-2 is 1 over 3, and wk-3 is 1 over 3. By combining these weights and the new set of states, we obtain the new set of particles given over here. This set of weights and the set of states is used in the next iteration of the particle filter. To summarize, the first resampling approach is to draw n state samples from the original set of states. The states are selected according to the probability specified by their computed weights. After that, the weights of the selected samples are set to the constant and equal value. That is, the weights of all the states in the resample set are set to 1 over n, where n is the number of particles. In Python, we can do this by using the function given over here. The first argument of this function, np.arange n, is the array of numbers starting from 0 and ending at n minus 1. Every number in this array is an index of a particular particle. This input argument denotes the set of indices from which we need to select n new indices. That is, this is the set used for resampling. Here, you should keep in mind that Python is indexing arrays starting from 0. The second input argument, n, means that we want to select n numbers from the set 0, 1, 2 until n minus 1. The third input argument, p is equal to weight values, is the probability of selecting a certain number in this set. That is, this array stores the probabilities of selecting a particular particle. The probability is equal to the array weight values storing the weight values for the particular particle. The output of NumPy random choice is a set of indices of selected particles. For example, for the first selected set, the output of this function is 2, 2, 1, corresponding to the states xk3, xk3, and xk2. That is, we can use the sampled set of indices to uniquely identify the selected states. This type of sampling is not the most efficient sampling method from the computational complexity point of view, as well as from the statistical point of view. A very popular alternative to this method is the systematic resampling method. Due to the brevity of this tutorial, we don't explain the systematic resampling method. We will explain the systematic resampling method in our future tutorials. However, we implemented the systematic resampling method in Python, and we will explain the function later on. To test the particle filter algorithm, we use a mass spring damper system explained in our previous tutorial. A link to that tutorial is given in the description below this video. The state space model has this form. The first thing that you should notice is that this is a continuous time state space model. The matrix A is defined over here, the matrix B is defined over here, and the matrix C is defined over here. In matrix A, we have three parameters, Ks, Kd, and M. Ks is the spring constant, Kd is the damping constant or damper constant, and M is the mass. The state space vector is given in the equation 22. It consists of two entries, x1 and x2. x1 is the position of the mass and x2 is the velocity of the mass. The next step is to discretize the state space model. To discretize the state space model, we use the backward Euler method. The backward Euler method approximates the state derivative of the state space model by using the backward finite difference discretization. That is, the first derivative of the state vector is approximated like this. Over here, h is a sufficiently small discretization time step. Now, by substituting this equation in the state equation of the state space model, that is, in this equation, we obtain this equation. Next, if we multiply this equation by h, we obtain this equation over here. Next, after several transformations, we can obtain this discrete time states equation. By replacing the approximation symbol in this equation with the equality symbol, and by replacing uk with uk minus 1 over here, we obtain the discretized state equation that looks like this. Here AD is defined here, and BD is defined here. The replacement of uk by its delayed version, uk minus 1, doesn't change anything qualitatively about our state space model. The output equation stays the same, that is, yk is c times xk. On the top of the derived state space model, in our simulation, we will add the process noise vector and the measurement noise vector. The goal is to estimate the complete state sequence x0, x1, x2, etc. of the discretized system by using only the time sequence of the output measurements y0, y1, y2, etc. That is, we want to estimate both the position and velocity of the mass by only using the measurements of the position. In the sequel, we explain the Python implementation of the particle filter. The first step is to import the necessary libraries. First, we import time, then we import numpy as np, then we import the plotting function. Next, in order to create a multivariate normal distribution from SciPy.stats, we need to import multivariate normal. As we explained previously, we will use two approaches for resampling. The first approach is based on the function numpy.random.choice. The second approach is based on systematic resampling. Here is the function that implements the systematic resampling. Due to the brevity of this video tutorial, we will just make several comments about this function. This function will be explained thoroughly in our future tutorials. The input to this function is this array, called weight array. This array stores the weights of all the particles. For example, if we have, for example, 4 particles, this array can look like this: 0.1, 0.4, 0.2, and 0.3. If you sum all the weights, that is 0.1 plus 0.4 plus 0.2 plus 0.3, you actually obtain 1. By using this set of weights and by using the systematic resampling approach, this function will produce a set of indices of resampled particles. To illustrate the selection, let us denote the indices over here. This weight corresponds to the particle number 0, this weight corresponds to the particle number 1, this weight corresponds to the particle number 2, and this weight corresponds to the particle number 3. This function might produce the output that looks like this. Since the particle with the number 1 has the largest weight, that is equal to 0.4, there is a 40% of chance that this function will select actually this particle. So the output can look like this: 1, 1. Then, let's analyze the other particles. For example, this particle has the weight of 0.3, so there is a 30% of chance that the function will select this particle. Consequently, here we will have 3. And over here, let's analyze the other particles. There is a 10% of chance that the function might select 0, and there is a 20% of chance that the function will select 2. Consequently, there is a higher probability of selecting 2, so the output can look like this: 1, 1, 3, 2. And this output is actually stored in this array. That is, this array contains indices of resampled particles. In our future tutorials, we will thoroughly explain how this function works. For the time being, you can type this function in your Python editor, and you can continue watching this video tutorial. Let's continue. The next step is to define the distributions. First, we need to define the statistics of the process disturbance. That is, over here we define the mean vector and the covariance matrix of the process disturbance vector denoted by wk or wk minus 1. Over here we define the statistics of the measurement noise. That is, we define the mean and the covariance of the measurement noise vector vk. In our case, vk is actually scalar. This is because yk is scalar. Next, we create the distributions of the process disturbance and measurement noise by using the function multivariate normal. The first input argument of this function is the mean vector, and the second input argument is the covariance matrix. The output of this function is the distribution object. We created two distributions. The first distribution, called process distribution, is the distribution corresponding to the process disturbance vector, and the second distribution is called noise distribution, corresponding to the measurement noise. Next, we need to define and discretize our test state space model. First, we need to define the continuous time state space model. Here we define the mass, the spring constant, and the damping constant. Next, we need to define the matrices A, B, and C. The matrix A is defined over here, the matrix C is defined over here, and the matrix B is defined over here. Next, we need to discretize our state space model. The first step is to select the discretization constant h. Over here, I choose h to be 0.01. The A and B matrices of discrete time state space model are defined over here. The matrix C stays the same. Consequently, here's how we define the matrix A, corresponding to AD over here, matrix B corresponding to BD over here, and the matrix C stays the same. Next, we need to simulate the dynamics of our discrete time state space model to get the test state space trajectory. That is, the true state space trajectory that will be used to compare the results obtained by the particle filter. First, we need to simulate the system. We select the simulation time. Over here, we will simulate the system for 1000 time steps. We select the initial state. Then we extract the initial state dimensions. Then we select the control input. I selected a constant control input. That is, I will simulate a step response of the system. I will obtain both the output and the state space trajectory. Next, we define this array that will be used to store the state space trajectory. This array will be used to store the output trajectory, and we set the first column of our state trajectory array to be equal to x0. That is, all the states, that is, all the simulated states will be stored column-wise in this vector called state trajectory. This for loop is used to simulate the discrete time state space model. I will zoom out my Python script so you can clearly see this for loop. Here it is. What do we do over here? By using this for loop, we are actually propagating this state space model over time. xk is equal to a xk minus 1 plus b uk minus 1 plus wk minus 1. And the output yk is equal to cxk plus vk actually only. Okay, so what do we do over here? Over here, we create a sample of wk minus 1. This part over here in the code is actually multiplication of b times uk. This part over here is a times xk minus 1. Over here, we actually sample the vector vk. Then, here, we perform multiplication of c and xk, and after we compute the right-hand sides, we store them in the corresponding arrays. That is, in this array and in this array. And that's it. And we do it recursively for different values of the index I. Next, we will explain the implementation of the particle filter. The first step is to create the initial set of particles. And here is our idea for creating the initial set of particles. We will create an initial set of particles that look like this. The states are actually points in an evenly spaced grid. Here's our grid. And this is our state space. State x1, state x2. Every point over here corresponds to the initial state. That is, for example, this point over here corresponds to the state x0, and notice over here that the 0 is the time index and the index of this particle is 1. Similarly, this particle is x0, 2. This particle is x0, 3. And this particle might be, for example, x0n. That is, this is the nth particle. We assume that all particles have equal weights. The weight value is equal to 1 over n. That is, the weight of this particle, denoted by W01, is 1 over n. The weight of this particle, denoted by W02, is also 1 over n. Similarly, the weight of this particle, W03, is also 1 over n. And finally, the weight of this particle, W0n, is equal to 1 over n. This is how we create the initial set of particles in Python. We use the initial state of the system. In practice, we don't know the initial state of the system, however, we know the initial guess. Consequently, over here, we generate the initial guess. Then, we use the numpy function, numpy.mgrid, which is short for mesh grid, to create the grid. Then, we reshape the points, and we create this matrix storing all the initial states. Let's explain this matrix in more details. This matrix of states has this structure. All the initial state samples are actually stored column-wise. That is, the first column corresponds to x01. The second column corresponds to x02. The third column is actually x03. And the last column is x0n. Next, over here we extract the dimensions of the matrix called states, and on basis of these dimensions we define an array for storing the weights. We set all the entries of this array to 1 over n, that is, to 1 over number of particles. Next, we select the total number of iterations for simulating the particle filter. In our case, it's 1000. Next, we defined and initialized two lists that are used to store the states and weights during the iteration of the particle filter. The list that will store all the state samples is called state list, and the list that's used to store all the weights is called weight list. We also initialize this list with the initial selection of states and weights. Here is the main iteration for the particle filter algorithm. Here is the first step of the algorithm. In the first step of the algorithm, we need to draw samples of xki from the state transition distribution. And here's how we implement this step in Python. I will zoom out the code so you can clearly see it. What's happening over here? To understand what's happening over here, we need to look into the state equation. The state equation is given over here. Here, we are just multiplying the terms on the right-hand side for sampled value of wk minus 1. That is, we first sample wk minus 1, and then on the basis of the knowledge of xk minus 1, uk minus 1, we simply compute xk. However, be careful over here. We do it in a batch manner. Because if you see over here, this term a times xk minus 1 is not simply a times xk minus 1, it's actually a multiplying the whole matrix, storing all the states, that is, the states of all the particles from the step k minus 1. Similarly, the same thing happens over here. This term, b times control input batch, is not simply b times uk minus 1, it's actually b multiplying a row vector storing all the inputs from the previous time steps. And over here, we draw samples from the distribution describing the distribution of wk minus 1. However, we don't draw a single sample, we draw the number of samples that's equal to the number of particles, as you can see over here. Next, let's explain the step number 2 of the algorithm. Here's how we implement this step in Python, and here's the formal statement of the step number 2. In step number 2, we first implement this equation. We compute the mean of this measurement distribution. The mean is actually C times xki. Then we construct the measurement distribution by using this code line. Then over here we update the weights, that is, we implement this equation. After that, we standardize the weights by implementing these two equations, and that's it. Simple as that. Next, we explain the step number 3. Here's the step number 3. And here's the formal statement of the step number 3. So what's happening over here? First of all, we need to compute this constant called n effective. Here's how we do it in Python. Then we need to check this condition. If this condition is satisfied, then we need to resample. Here's how we resample. And I will zoom out such that you can see this code line. I explained this code line at the beginning of this video tutorial, and I will just briefly repeat the explanation. So what's happening over here? This function will take as the first input this array that will store all the possible indices starting from 0 and ending at n minus 1. That is, all the indices of the particles. The second input argument of this function is the number of elements that we want to select from this array. In our case, we want to select number of particles elements. That is, this function will draw n samples from this array. And over here, we specify the probability of selecting a certain index. The probability is actually equal to our weights. And that's it. This is a simple approach for generating indices of resampled particles. That is, these indices will be stored in this array. Another approach is to use the systematic resampling, and we explain this function at the beginning of this video tutorial. Here it is. Here's the function. After we select the new indices of new samples, we need to generate new states, and we do it like this. After that, we need to reset all the weight values to 1 over n, and we do it over here. Next, we update the states and weights for the next iteration, and we memorize the states and weights, and that's it. Simple as that. Let's repeat. Here's step number 1. Generation of the samples xki. Step number 2, update of the weights, and the step number 3, resampling. And that's it. After we compute all the state samples and all the weights of all the particles, for every time instant k, we need to extract the mean trajectory. For fixed value of k, the mean state is computed by computing the sum on the right-hand side. That is, the mean state is simply a weighted sum of the weights and the corresponding state samples. This is how we compute the mean state trajectory in Python. First, we define an array, or better to say a matrix, that will store all the state estimates for different time steps k. Then, we use this double for loop to compute the mean state at every time instant k. Let's now run the complete code until here. It will probably take some time on your computer to run this code. In my case, the execution time is around 3-4 minutes. Okay, now the code is running and we need to wait. The final step is to plot the results. First, we will plot the true and mean state trajectories. We do it for state x1 and state x2. First, we define a figure, then we plot the mean state trajectory, we set the color, line width, and we set the label. Then, we plot the true state trajectory, we set the color, line width, label, then we add the title, then we add X label, Y label, we set the size of the fonts, we save the figure, and we show the figure. And we do the same thing for the second state. Notice the difference between here and here. The only difference is in this index. You can see the index 0 corresponding to x1, and the index here is 1 corresponding to x2. Okay, so let's run this code and let's see the outputs. Okay, looks good. This figure over here shows the mean estimated state, that's the red line, and the true state x1. We can see that the mean estimated state converges very quickly to the true state. However, you cannot have a perfect match between the true state and the mean estimated state. This is simply because you always have a stochastic term, wk-1, that is, you always have a process disturbance affecting your state dynamics as well as the measurement noise affecting your output. That's why you can never have a perfect match. However, you can see that our particle filter is actually tracking our true state very well. This is the figure for x1 and this is the figure for x2. Similarly for x2, we can see that our particle filter converges after maybe 10 time steps. These are very good results actually. Next, we need to explain this important for loop. This for loop is used to generate a series of PNG images. When you connect all these images together, you can get this amazing animation. Let's briefly explain this animation. On the horizontal axis, we plot the coordinates of x1, and on the vertical axis, we plot the coordinates of x2. That is, every point on this graph represents a state. The red circle, and you can see how the red circle is moving, is our true state. The other circles having different colors represent the particles. The radius of the colored circle are corresponding to the weight value. The higher the weight value, the larger the radius. Let us now stop this animation and explain how this animation is generated. If we freeze this animation, we will actually obtain a single PNG image. And this PNG image is generated by using a single iteration of this for loop. We use the scatter plot to generate these circles. This code line is used to generate the red circle. That is, it's used to generate the true state. This part over here is used to generate the particles. Over here we set x and y limits, we set the labels, and we set the size. And finally, we save the figures. By running this for loop, you will obtain a set of 1000 PNG images. And this is how PNG images. The next step is to use a software for gluing these PNG images. In my case, I use Blender. I created a separate video tutorial that explains how to glue all these images together. A link to that tutorial is given in the description below this video tutorial. Okay, that would be all for today. I hope that you liked this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.